Welcome back. We are continuing our discussion of Edmonds' algorithm for finding a matching in a non-bipartite graph, a maximum size matching. And a brief summary of what we've said so far. We have our graph, we have our matching M, and we're looking for an augmenting path. And X is the set of exposed vertices that are not covered by the matching. And we have talked about in the previous lecture this idea of M alternating trees and also maximal M alternating trees. And in the last lecture, we mentioned, first of all, not only the definition of all of these things, but also we gave a key lemma, which I'll just repeat here so that you don't have to flip back to the previous lecture. And it says the following. What can happen when we add M alternating, when we start growing our M alternating trees? Well, we're either going to find an augmenting path, in which case we add it and repeat, or somehow the process stops. So the question is, if it stops, can we say that we are done? Can we assert that M is maximal? And so the lemma that we gave at the end of the last lecture is a sufficient but not necessary condition for when we can stop. So if the algorithm in the previous lecture for growing an M alternating, for growing M alternating trees, maximal M alternating trees, maximal, not maximum, and, well, first of all, it did not find an augmenting path. That's kind of the obvious part. It did not find an M augmenting path. And then also, here's the key. There are no edges between vertices labeled E. Then M is a maximum size matching. So let's look back at our example, and just to see how this how it compares to that. So remember that we had this is in a way our kind of running example in this set of lectures, where in yellow I'm going to mark down our current matching M, and therefore that means that there are two exposed vertices. And let's grow the tree by so this is our exposed vertex. So so what happens in the tree, I'm going to add all edges that I can. So this is labeled E. This is labeled O, O, and O. From here, I add necessarily these edges, these single edges. And now this is labeled E and E. And that's all I can do. The algorithm terminates at this point because there is nothing, I'm only allowed to extend the E nodes. And so you'll see in this example, this illustrates the lemma. It is not a maximum size matching. We know that. We've seen already how we can extend it. And also the statement of the lemma is not satisfied because I have indeed an E to E edge. Note that this edge is not in the tree. So I never add an E to E edge when I'm growing my tree. So it's a little bit, we need to keep straight what edges we're talking about. I grow my tree and then I look and I say, are there some other edges that I never added that are between E and E? And in this case, the answer is yes. And therefore, 2 is violated, and so this lemma correctly does not assert that this is a maximal matching. So let us now prove this this lemma. So again, this illustrates that this is a sufficient condition for showing that M is maximal. In other words, when I say sufficient condition, it means that when we've terminated, we know that if this is satisfied, it shows that our lemma is, that our matching is optimal. Okay, so let's give the proof of this important lemma, and it has basically 3 parts. So first, note that any edge in the graph, not just the tree, any edge in G with an endpoint in E. And now I notice also that I'm overloading notation a little bit because I did use E to denote the full set of edges in the graph, and now I'm using it to denote anything labeled E. So I'm not sure what I'm going to do. I guess I'll leave it to you to keep track of that. So again, this is, by this we mean the set of nodes labeled E. Okay, so any edge in G with an endpoint in E must have its other endpoint in O. This is O meaning odd. This is obvious because that's the assumption. There are no edges from E to E. So if I have an edge that starts in an E, then if property 2 is satisfied, then obviously it ends in E. And so again, it's because E to E is ruled out by assumption, and the possibility that E connects to some other node that I have not yet added to a tree and therefore has not been labeled is ruled out by maximality. So I'll just write E to other is ruled out by maximality of the tree. So did I write? Yes. So this lemma is for maximal trees. Again, it means that I'm not able to grow this anymore. Okay, so what does this very, very simple observation tell us? Actually, it tells us something pretty important, and it tells us that I've completed this process. It tells me that the number of even nodes is equal to the number of odd nodes plus the cardinality of the exposed vertices. And again, this is because I didn't find an augmenting path. So this means that, this is again because there is no M augmenting path. That was also an assumption. And all paths, therefore, because they start in X, any path can't end in X. It can't end it can't end in O. All paths end in E, in an even node. Again, why is that? Because I started an even node. This is the root. and I go to an odd node, and then I go to an even node, if I were ever to stop at an odd node, then this is an augmenting path. So I can't stop at an odd node. So this cannot happen. So all paths end in E, and all even nodes, so all even nodes except for root nodes of the tree are matched to odd nodes by an edge in M. So again, the picture kind of tells the whole story. Here's R, and I don't know, what does it do? Maybe it branches initially to 2, but you know, each one of these, so this is even, so except for this even node, every odd node is matched to an even node. And even if one of these branches, well, all of these are odd nodes, so they're again matched. Right? So for every even node, we have an odd node. Here's an even node, there's an odd node. Here's an even node, it came from somewhere, it was an odd node. And because it came from exactly one, so even though there's this branching is allowed, just the simple counting tells us that we have this very simple accounting. So all the even and odd are matched except for the root nodes. So what is this basically? What is this basically telling us? This is telling us the following. It's giving us this nice result that says that if at the end of the day, I complete my maximal tree, and I have all of my even nodes over here, and I've got all of my odd nodes. And when I draw it this way, what is the assumption of this theorem telling, of this lemma telling us? It's telling us that I may have edges, that I have edges like this, and I may have edges between odd and odd, possibly. Again, just keep in your mind, what I'm drawing here are edges in the graph, not edges in the maximal tree, not just edges in the matching. These are all of the edges in the graph. And the maximal tree has just labeled even and odd. So, and so you can see that what really the assumption of the lemma is telling me is that I have a partition between E and O like this, and moreover, there is a matching, and the matching runs from E to O. But now the result of the lemma is immediate, because if I have found some coloring or some labeling of the nodes into E's and O's, then I essentially have reduced to a bipartite matching problem. In a way, it's not bipartite, but the same spirit holds, and it's now clear that this has to be a maximum size matching, because I have no edges between E and E. I have only edges between E and O. Yes, I have edges between O and O, but who cares, because every single node in O is already matched. So you can see that there is nothing I can do to help my friends here. It just is what it is for them. Because if they're only connected to the right, then, well, there's patently nothing different that we could have done in order to increase the size of the matching. And so it's actually a very, very simple result, but we're going to see that it's powerful. I want to belabor one point. This is not a decomposition result for graphs. It's not saying that any graph we can find a labeling into E and O that has this property. And so in fact, most graphs are not like this. It's just saying that if you happen to have a graph like this, then you're in business. So again, it's saying that if we make our maximal tree and we end up in this situation, this is a certificate for maximum sizeness of our matching. Just checking against something that we've already seen now in a number of ways. Basically, for bipartite graphs, when you start growing your maximal trees, you will always end up in this situation. You will never get stuck. Whereas, as we saw in this example here, this example shows that we have a matching that is not maximum in a non-bipartite graph, and the maximal tree did not have this structure. But for bipartite graphs, this cannot happen, and it cannot happen because we already have this partition naturally. So just to write this down in a theorem, if our maximal alternating tree so if our algorithm for maximal M alternating tree trees finds a collection of trees without terminating at an M augmenting path, in which case we just augment, then M is maximum size. Again, the intuition is simple, is that there are never going to be even to even edges in a bipartite graph. You can never end up, no matter how you grow your maximal trees, an even to even edge implies that you have an odd cycle. But I encourage you to work out all of the details as an exercise. Okay, so we've got our characterization. That says we grow maximal trees, and with the algorithm described in the previous lecture, if you have no even to even edges, you have a maximum size matching. So, well, our problem exactly is now the setting where we do have even to even edges. So let me draw you the picture that you'll basically see anywhere in any textbook that describes Edmonds' algorithm, and it's also suggestive. So here is our picture, and this is an even node, this is an odd node, even node, odd, odd, and these are even and even. And what could happen here? So we this is just a part of the tree that I'm going to grow, that I'm going to talk about. There could be other edges coming off of here. There could be this edge here, which I'm not allowed to add, okay, because it's not a tree. And there also could be, other edges off of these odd nodes. But as we've mentioned before, whenever we get to an odd node, we don't branch. We just add what's in the matching. Okay. So some terminology which is just suggestive. This is supposed to look like a flower, and you can see that here there is an odd cycle because we have an even to even edge, and this is called the blossom. And so therefore, in order to continue the description here, the descriptive naming, this is called a stem. And the key to Edmonds' algorithm is contracting the blossom. Let me call this blossom B. Contracting the blossom, which means that I'm not going to, and I'm going to denote it in this way. So I'm going to form the graph And as we do sometimes in linear algebra or abstract algebra, this is not I'm not subtracting, I'm not deleting the edges by in B, the nodes in B. I'm creating essentially an equivalence class. This is what this notation, the forward slash, often denotes. And that's exactly what I'm doing here. You can think about it in the same way as when you think about a modular space. So I'm identifying every node in the blossom. And so what happens when I contract it? I have my R, O, and then this node here is my contracted blossom. And I need to keep track of all of the edges. And so if I'm contracting this, I still have, as in this picture, 4 potential edges. 1, 2, I'm kind of drawing them, I'm trying to draw them at the same angle, so it's kind of suggestive. And what is the key that we observe? The key thing that we observe is that contracting a blossom, first of all, does it allow us, does it mess with the continuation of the tree along these edges? No, it does not. Because you see, I was at an E here, and I came out at an E, and so I could continue in exactly the same way. But it does something else really important. It's changed the parity of this node, because this node collapses into an even node. So this edge here that I was not allowed to explore previously, I am allowed to explore. And that means that we can now grow the tree in new ways. In particular, I can grow it along this edge and this edge, which I was not allowed to grow before. So this is the key idea. We're going to stop now, and we're going to continue on in the next lecture with the proof that shows that this key idea is coupled with the previous lemma is what we need in order to come up with an algorithm that finds maximum matchings.